Mathematical modelling is the title we give to formulating problems in mathematical terms and then solving them by the use of mathematical techniques. During the course of this programme, I shall be filling in this blank diagram to bring out the structure of the process of mathematical modelling. And in order to do that, I shall be using an example from operational research. Operational research, you might say, is the application of mathematical modelling to the problems of management. In this case, it's a management problem for the National Coal Board. You may think that all the Coal Board does is to dig coal. But in fact, they're the biggest purchasers of engineering equipment in the country. Every year, they buy over £500 million worth of stock, from nuts and bolts to large power machinery.
54-inch belting. So we've got the gear up now for Easter. There isn't a lot of time. It's going to mean complete new receiving hopper at that end to receive the main transfer station.
So how do they organise this purchasing? And how does mathematics help them? The spearhead of the coal board's operation is the pit. There are 250 pits in the coalfields up and down the country, from Scotland to South Wales and Kent. And the pits draw their equipment from 24 central stores located conveniently for each coalfield. We went to the stores at Alloa in Scotland to look at the scale of their stockholding problem. Alloa Central Stores is one of the largest in Britain. It supplies equipment to the coal board's Scottish area. There's 70,000 square feet of storage area here. And the items in stock range from nuts and bolts through conveyor belts to bulldozers. In all, over 36,000 different items are stored here. Every week, hundreds of different articles are sent out to the pits and workshops in Scotland. When stocks get low, new supplies have to be ordered from the manufacturers. But how do the coal board manage their ordering? How do they decide how much of an item to order or when to put in a new order? With millions of pounds involved each year, they must have a system for ordering. C.L. Templeman is the Director General of Purchasing and Stores Department.
It is a massive problem, and if I can illustrate it by saying that we have no less than some 1 million individual stock records spread over some 250 stock holding points, that will tell you how big it is. It is so formidable that we've had to have a veritable army of clerical staff to operate it, and we have had to have a tremendous investment in stock. Indeed, it was always going to get more difficult as the industry became less labor-intensive and mechanized more. It was clearly necessary to find some simpler and more effective way of dealing with stock control. And our first thoughts that we might be able to devise some lookup tables which could be prepared and used by the staff to enable them simply to read off the quantities that we should order and the levels at which the reordering should take place. It was a major breakthrough, and in 1972 the second breakthrough occurred when we extended computerization of our procedures to this aspect of our operations. The mathematical model was converted into a computer program, and from then on it was merely a question of having to feed in movements on the various stock accounts, and the computer would automatically produce order suggestions.
There are computer terminals at the Alloa stores linked to the coal board's central computer. Each punch card signifies one item leaving the stores for a coal mine. This card might be for conveyor belt fasteners. It's the operator's job to compile a punch tape, which is the input data for the mathematical model. computer then uses this data and the model to calculate a reorder quantity. The results are printed out and checked before they're used for ordering. But just how does the computer do this? We're obviously talking about a very big problem, and it's a very real problem. It's not a textbook exercise. And of course, it's a problem to which the people in operational research at the National Coal Board have devoted a great deal of thought. But let's think ourselves back and see what we could do if we started from scratch. Well, I think the thing that we do, first of all, is to try and isolate some of the important quantities in the problem. And one important quantity would be stock level. If we were to simply observe how the stock of one particular item changed with time, what might we see? Well, I think it might be something like this. Stock diminishes as orders come in from the pits, and every so often a new order arrives to replenish stocks. So by observing reality, this might be the way in which we discover that the stock level of a certain item varies with time. And the first thing I'm going to do is to abstract from that. The first item of abstraction is to replace this, which represents the usage of the item, by a uniform usage, in other words, by a straight line. And so I would obtain something like this. And then I'm going to abstract even further than that. I'm going to idealize the problem even more. I'm going to assume that these, which represent orders coming in to our stores, are all equal in size, and that they're all equally spaced in time, and that we allow stocks always to run down to zero before restocking. And the result of all those assumptions is to get something like this. And that's the problem that I'm actually going to solve. It's very much a simplification of reality. And you can probably even think of some more ways in which it doesn't correspond to reality. In fact, you may be wondering, have we got a problem left anymore? Well, we have, because the size of these saw teeth is at our disposal. You see, we can do this. We can order in very small quantities, very often. Or we can order in very large quantities, very infrequently indeed. And the key to that is the cost of the whole thing. To find out what are the components of the cost of stock control, we talked to a member of the Coal Board's Operational Research Executive, Mrs. Elsie Cropper.
Well, we have to decide on order quantities so as to minimise all the costs involved. Of course, the quantity which is appropriate to particular items will vary, depending on how many we use and how much they cost. We'll take, for example, screws, which are a very high demand item. We obviously wouldn't order these in singles because every time we place an order, there's an associated charge of 25 pence, and so we would choose to order screws in bulk. However, if we're talking about heavy equipment, if we chose to order this in bulk, it would take up a lot of space and tie up a lot of capital. And so we have to consider holding costs in this case. The holding cost represents storage and interest charges. And in the board, we estimate that each year the holding cost is about 17% of the average stock value.
And 17% of the cost of one of those bulldozers is really an enormous amount of money. Obviously, we're not going to order those in dozens just to cut down on ordering costs. But for every item, those are the two costs that are involved. There is the ordering cost, the cost of actually processing an order through the administration. And then, secondly, there's the holding cost, which is not the cost of the item itself. It's the cost of the capital tied up, the interest on that capital, or the amount of money that it could be earning if it could be employed elsewhere. And those are the two contributions to the cost. And they pull against each other, these two costs. Because if we try to keep down stock levels, then what we find is that by having low stock levels, in a given interval of time, we're going to place an awful lot of orders. So we're going to get high ordering costs. If we want low ordering costs, we place our orders a good deal less frequently. But in this case, what happens is, of course, that our stock levels are generally very much higher than they were here. What's the trade-off between these two costs?
We've already discussed the influence of order cost and holding cost, and the simple stock control model takes into account just these two costs of ordering and holding. As the size of the order increases, the order cost will decrease. This is basically because we're placing fewer, larger orders. However, if we look at the holding cost, as the size of the order increases, the holding cost will also increase, basically because we're increasing our average stock.
And these are the two graphs. And it's at this stage that we start to convert our problem into mathematical symbols. Here's the first graph showing how the annual ordering cost goes down with the order quantity. But why this sort of shape? Well, suppose the annual usage is U items. And suppose in each order we have Q items. Then how many items a year will we actually order? The answer is U over Q. Think about a numerical example. If there are 100 items used per year, and we order them in batches of 20, then we shall place 5 orders. And each of those will cost 25 pence, remember? That's 0.25 times U over Q pounds as the annual ordering cost. And you see that this graph is simply 1 over Q times a constant. In other words, it's a 1 over X type graph. Now, the other graph, which shows annual holding cost against order quantity. In this case, if the order quantity is Q as before, and P is the price of an item, then this all depends on the stock level that we've got. Now, what is the stock level? Well, if we order in amounts Q, then you can see that the average stock level at any time is a half Q. A half Q is the average stock we've got at any time. So it's a half Q multiplied by the cost of holding an item in stock for a year. And that's 17% of its price, so 0.17p times a half Q. And in this case, this is just something times Q, and so the annual holding cost as a function of order quantity gives a straight line graph. But of course, it's the sum of those two costs that we're interested in. We're interested in how this changes as Q changes. And we can find out that simply by adding together these two graphs. This graph is the sum of the other two. And you see, this new graph does have a minimum. Now let's look at this problem analytically. This is the expression for the total cost Y. To find the value of Q that leads to a minimum of Y, we need to look at the derivative. The derivative with respect to Q. So by differentiating the two terms, we get these. When we now set dy by dq equal to 0, we get an equation for Q. And after a bit of algebra, we get this value of Q. This is the appropriate choice of the reorder quantity to give the minimum total cost. But remember, I said we were going to use this problem to bring out the structure of the process of mathematical modelling. So let's have a look at what we've done so far. we started with a real problem. And out of this real problem, we idealized, by simplification, by simplifying assumptions, a model like this. Having got that model, we then converted that to mathematics. And we set up a mathematical problem to minimize this. And now we've arrived at a mathematical solution to that problem. So here's the solution given by this formula. But it's a very long way from reality, in fact. Reality is way over there. And the first step in getting back to reality is perhaps to interpret this solution. Here's our formula. It says the reorder quantity is given by this. Now, the 0.25 is, of course, the ordering cost. So that's where that came from. And then U was the annual usage. And the 0.17p is, in fact, the holding cost. It's 17% of the price of the item. And let's just see if that formula does agree with our intuition about what should happen. If p is very large, then that formula says that the reorder quantity will be very small. And that does agree with intuition. If you have very, very expensive items, you will order them in very small quantities. Whereas if p is very small, it says the reorder quantity will, in fact, be large. And we shall order cheap items in large quantities. So it does agree. Let's now simply put in some numbers and see what happens. If we have, let's say, a box of sort of special screws for which the demand and usage is 45 boxes a year. And suppose the price of each of those boxes is £2.41. Then if we put that simply into the formula, we get a value of Q which is 7.41. And the interpretation of that is that we should all order in that size of quantity. But, of course, you can't usually order 0.41 of a box of screws, so that might be rounded off to 7. And so the solution to that particular case of this general stock control problem is order 7 boxes at a time. But what's it the solution of? In fact, it's the solution, of course, of this simplified model. And when we've got to this stage, perhaps what we should be saying is, can't we take into account some of those factors that we left out when we arrived at this simplified model? Let's see what the coal board does.
Our routine is rather more complex than the simple model because we've taken other factors into account. For instance, the simple model assumes that orders arrive instantaneously. Well, in reality, of course, there's a certain time lag between an order being placed and that order arriving. This means that as well as calculating an order quantity, we also have to calculate when to place that order, known as the reorder level. If we type in the characteristics of an item, then we can see that our calculations would give us a reorder quantity of 9. The square root answer for this same item is 7. So we see that because we're taking extra factors into account, the answers are slightly different. However, we do use the square root formula in all our calculations as our first estimate of the quantity.
So you see, our little bit of mathematics is, based on this simple model, is at the heart of the coal board's model. But what did she say? As our first estimate. In fact, it's an invitation for us to introduce extra factors here and to go around this process again. Now, I'm going to ask you to look at some of those factors in the follow-up work to this program. But let me just give you a very quick hint of some of the things. First of all, there was this business of lead time, the gap between ordering and actually getting the goods into the store. How does that affect our model? Well, actually, in this model, we've ignored the lead time. We've assumed that you place an order there and instantaneously jumps the stock to there. If there is a time gap, then all we have to do is measure that time gap back from that point and order when our stock level is here. In other words, there will be a reorder level given very simply by that. And the rest of the mathematics in all this is unchanged. So our first introduction of one of the extra factors doesn't change the reorder quantity. The thing that does change the reorder quantity is the next one, which is taking into account the cost of running out of stock. Now you may say it would be silly to deliberately build in the idea of running out of stock, but it's not so silly. The difficulty is in putting a cost on running out of stock. But if you have a cost on running out of stock, then the model changes like this. Stock, variation with time, goes something like that. And here we're in stock, and here we're out of stock. And what happens now is that there is a cost associated with our holding of stock here, which is less than it was before because our average stock that we're holding is less. But that's got to be balanced against a cost of falling below the zero line here, in other words, the cost of being out of stock. In the mathematics, what happens is that those two terms are replaced by three terms, an extra cost due to running out of stock. But the mathematical problem is still solvable, and you can go through to the mathematical solution and to the interpretation of that solution. But finally, perhaps the most unrealistic thing you may feel is the assumption that we made right at the beginning, and that is that the usage is uniform. If you want to take into account variable usage, in other words, a random demand from the pits for these items, then, of course, you're into probability and statistics. And in fact, the coal board's model does include probability and statistics. The model is more complex, it leads to more complex mathematics, a more complex mathematical solution, but it gets us closer to the real problem that we're trying to solve. And in this case, I haven't said very much about this box, the comparison with reality. In this case, our real test is the usefulness, I think, of the solution that the model, in this case the coal board's model, comes up with. And to say something about that, I think we ought to go back to the Director General of Stores and Purchases.
Well, we watched the outcome of this with interest when it was first introduced, and we were delighted that it appeared to operate very satisfactorily over a wide range of commodities. It certainly brought a speed and discipline to the ordering process which had hitherto been lacking. And this in turn enabled us to give a much improved supply service to the board's collieries and to the overhauling, repairing workshops.